So by now we know some wacky things start happening when we approach the speed of light. And today we're going to look at specifically how these things change as we approach the speed of light. So how time intervals change, length changes, mass changes, and momentum changes. So first of all, we have an object that's moving 0 meters per second relative to you. How does that differ from an object moving at, say, 10 million meters per second relative to you? How are these things going to differ? So first of all, we can look at time intervals. So let's pretend these are two separate spaceships. One of them is moving at 0 meters per second, just floating there in space, and one of them is moving at 10 million meters per second. So pretend you're on this first spacecraft that's not moving. Say you take out a stopwatch and measure a time of 10 seconds. Now, as this other spacecraft zooms by, if you could sort of look into that spacecraft and see a clock on that spacecraft, what it would look like to you, it would look like that time has basically sped up for it. So if you could see in that same amount of time that you timed 10 seconds, you might see that a same stopwatch on the other ship maybe goes by something like 30 seconds. It's not going to be exact, I just sort of made up these numbers. You could actually calculate it, and we're going to calculate it later. But the important thing is more time will pass on that second spaceship, according to you looking at it from your spaceship in that same amount of time, which is a bit strange. This is called time dilation. And basically, if an object is moving relative to you, it will experience time, or you will see it experience time at a faster rate. So again, that's called time dilation, and the equation we can use to express that is a time interval of a moving object is equal to this factor called gamma, which is a Greek letter G, and it looks sort of like that. So this is gamma times the time that you observe from a stationary clock. We'll talk about what gamma actually is later and how to calculate it, but for now, it's just some factor. And the other thing to realize is that the factor is always going to be greater than 1. So that's our time interval, so that's how time behaves. If we were to look at the length of the spacecraft, so say you're in the same model of spacecraft that's zooming by you at 10 million meters per second, let's say the length of this spacecraft is 10 meters. Even though you know that the one is zooming by you super fast, it's the same model of spacecraft, so it should be the same, you might observe, well, you're going to observe, that it actually appears shorter. It contracts due to sort of space-time wonkiness due to special relativity. So we might observe it as, I don't know, I'm just going to make up another number, 8 meters. So it actually looks like it gets shorter. So you'll notice it's the opposite of time. Time is like directly related to it, where time increases as the object moves faster, or a time interval gets longer as it moves faster. Length actually decreases, which is why the relationship is you're dividing by gamma instead of multiplying by gamma. And the next one is mass. So say you know, again, the same spacecraft, you know your spacecraft has a mass of, let's just say, 10,000 kilograms. What happens when something goes faster and faster and faster relative to you, it's observed to have more mass. So it might have a mass of, 13,000 kilograms. And again, it's going to be this gamma factor that's going to determine that. So you just multiply this gamma factor by the stationary mass. And then lastly, we have momentum. Mass and momentum are closely related to each other. And that's sort of the same relationship, where something with a momentum, a stationary momentum, if it's moving fast, it will appear as though the momentum increases. And that's mainly because the mass increases. So remember, all of these facts are necessary in order to make the speed of light appear constant from any observer's point of view. These are just things that come out when you do some math involving that. So it's sort of counterintuitive, but it's because we usually don't, observe things that move very fast. So we're going to do a problem now. And again, I haven't really talked too much about this gamma, but it actually has a special name. That factor, that gamma, is called the Lorentz factor. And we're going to learn how to calculate it on the next page, but for now, let's just keep it simple. So in this question, I'm just saying, assume that that gamma factor is 2. How would these things behave? So, by the way, a gamma factor of 2 means that an object is moving very fast compared to the speed of light. It's a very large percentage of the speed of light. So it's not moving at the speed of light, but it's moving very, very, very fast. So if the spacecraft is 40 meters long, has a mass of 6 times 10 to the 4 kilograms, and starts, the speed is 2, what is the length as observed from Earth? So the length will dilate, right? Or contract, it'll get smaller. The length of the moving object is just going to be the length of the stationary object over gamma. You'll notice your textbook, by the way, uses M and S for the subscripts, which just means moving and stationary. So if we do this, all we need to do is the length of the spaceship, which is 40, divided by 2, which is our Lorentz factor, which gives us a length of 20. So we'd observe it basically contracting by a factor of 2. So it looks 20 meters long as it zooms by. What would its mass be? Well, its mass is going to increase, right, if it's moving. It's going to be gamma times m stationary times the stationary mass, or sometimes we call that the rest mass. So it's just going to be 2 times 6 times 10 to the 4, which will be 1.2 times 10 to the 5 kilograms. So basically double in mass. And lastly, an interval of 10 minutes on Earth would feel like for the astronauts on the spacecraft if you were to take out stopwatches and you were to look at a clock on that spacecraft. You're basically able to magically see into that spacecraft and see the same amount of time that's 10 minutes for you, it would be doubled. So Tm is going to be gamma times, I'll call it delta t because it's a time interval, times delta t stationary, which just equals 2 times 10, which is 20 minutes. Okay? So that sort of gives you some sense of what moving very, very, very fast can do. A few more little notes. We call this the moving and the stationary. It's sometimes referred to as the rest instead of stationary. We sometimes call this the rest time interval, or the rest length, or the rest mass, or the rest momentum. Those are common terms that you see. And we also sometimes call the moving ones relativistic. So that would be the relativistic time, the relativistic length, etc. The relativistic mass and the relativistic momentum. Those terms are just, used in the same way. I just want to point that out. The reason why I think the textbook doesn't use that is because they both start with R, and it would be an annoying subscript. So they use M for moving and S for stationary. All right, moving on. How do we actually calculate this Lorentz factor? Well, the Lorentz factor is, if you do some crazy math, actually the math isn't too bad for this. Your textbook does a proof of this, basically using the Pythagorean theorem. It's not actually crazy math. It's sort of cool that it's so easy to calculate. But this is the Lorentz factor. So it's 1 divided by the square root of 1 minus v squared over c squared. So you see the only thing you really need to ever plug into this equation is the speed, v. And because c is a constant, right? C, we often call that the speed of light. It's the fastest speed that something can go in our universe. And that's 3 times 10 to the 8 meters per second. So that's a constant. So the only thing we need to plug in ever is v. So what does the Lorentz factor look like for these different values down here? So for example, for 10 meters per second, all you would do is plug in 10. And then there you go, 3 times 10 to the 8, all squared. Don't forget to square the speed of light. So if you actually plug this into your calculator, I don't know about you, but my calculator just tells me 1. Which is a bit strange because we're doing all these complicated things, but let's look at what we're actually doing. We have this 10 squared here, but we're dividing it by this ginormous number, right? It's going to be 3 times 10 to the 8 squared is like saying 9 times 10 to the 16. So that's going to have a lot more zeros than what's on top. So basically, if you're dividing a small number by a much bigger number, it's going to be about 0, very close to 0. So you're basically doing 1 minus 0, which is just 1. And 1 over the square root of 1 is just 1. So this basically comes out to 1. The Lorentz factor is 1. And if we think about what that means, if we look at our relativistic equations here, if gamma is 1, or very close to 1, our moving and our stationary times are going to be about the same, right? Just like our lengths, our moving and our stationary lengths are going to be about the same because you're just dividing by 1. And same with mass and same with momentum. So they're going to be about 1. So that's why, when we're moving at slower speeds, like 10 meters per second, you don't need to worry about relativistic time or length or mass or momentum because that Lorentz factor is so small. Well, so close to 1, I should say. So if we do the same thing for 1,000 meters per second, is that still going to be 1, or is that going to be something different? So I don't know about you, but my calculator is still telling me it's about equal to 1. It just says 1. It doesn't actually give me 0.0000000. It's actually something slightly above 1, but even at 1,000 meters per second, it's not big enough to make any noticeable difference in those factors. Now let's speed up. Let's say we're going at 10% the speed of light, or 0.1 c, right? That means 10% the speed of light. So if we plug that in, we'll actually show the calculation here. 1 over the square root of 1 minus 0.1 c over c squared. This is squared as well. So if we do that, first of all, this one's easier because hopefully you realize that the c's are going to cancel out, right? This c squared and this c squared are going to cancel out. We still need to remember to square the 0.1, right, because that's inside the brackets, but we don't have to worry about the c. So we don't need to plug in that 3 times 10 to the 8 meters per second. So if I do this, what does it give you? So that gives me 1.00504, etc. So that's something that's bigger than 1, but even that 10% of the speed of light, right? It's 1.005. So that's only a 0.5% increase in mass or momentum, or a 0.5% decrease in length, right? So even that fast doesn't have a huge impact. What about if we're moving at 99% the speed of light? What would that come out to? So that comes out to 7.1 approximately. So now we're talking, now we have some big numbers. If you're moving at 99% the speed of light, we're going to have a length contraction of 7 times, about 7 times, right? Or a time dilation of about 7 times. And the mass is going to increase by 7 times, and the momentum as well. What if you're moving at c, at the speed of light? What's that going to give us? Well, if you look at the equation, it's going to be c squared divided by c squared, which is just 1. So this is going to be 1. It's 1 minus 1. So 1 minus 1 is 0. So it's the square root of 0 in the denominator. So 1 over 0, you can't divide by 0. So in this case, gamma is undefined, right? You can't have and the thing is, you can't move at the speed of light. As you get closer and closer to the speed of light, this Lorentz factor is going to go up and up and up and up, but it's never going to reach the speed of light because, it's sort of like you would have a Lorentz factor of infinity, which doesn't make sense. The math falls apart there. So gamma is undefined at the speed of light. So that's why the math tells us that we can't move at the speed of light. What happens if we're moving faster than the speed of light, 1.1 c? What you'll notice is if you do the math, this thing down here is going to turn out to be negative. And something you should remember from math is you can't do the square root of a negative thing. So again, because of what's under here, if we're moving faster than the speed of light, it is also undefined. So we're sort of cut off. We're cut off here, right? We can't go we can't go the speed of light, we can't go faster than the speed of light, and that's what the math tells us. So we could keep putting in 9s here. We could do like 0.9999999 c, and this value would keep going up, but we can never put in c, okay? So let's do one more example. A 1,200 kilogram alien spacecraft passes by Earth with a speed of 0.25 c. Determine its momentum relative to Earth. So this is one we didn't do in the previous page to calculate a relativistic momentum, but what it is, well, the equation is this. The relative momentum is gamma times the stationary momentum, or the rest momentum, right? We know we're given in this question that the speed is 0.25 c. So we can calculate the gamma for that as, the gamma for that as 1 over the square root of 1 minus 0.25 c squared over c squared. And if we do that, the c's are going to cancel out again, but we still have to square the 0.25. So we're going to get 1 minus 0.25 squared, take the square root of that, 1 over that. So this is 1.0328. I'm just rounding to a bunch of significant digits. We'll round at the end. So basically 3% is our difference, right? 3.28%. So our momentum, our rest momentum is going to be multiplied by that number. So we need to actually find our rest momentum, right? We don't know what our momentum is, but we do know that momentum is mass times speed. So we actually need to calculate the rest momentum and then multiply it by that factor. So we'll call this the PS, right? So the momentum is the mass, which is 1,200, times 0.25 c. So 25% the speed of light. And we know the speed of light, so we can plug that in. 0.25 times 3 times 10 to the 8 meters per second. So we can calculate our momentum there. Our rest momentum, this is as if relativity didn't exist. What would the momentum be? It's 0.25 times 3 times 10 to the 8, which gives us 9 times 10 to the 9. And that would be kilogram meters per second, right? And now that we know that that's our rest momentum, all we need to do is plug that into our equation for the relativistic momentum, which is going to be 1.0328 times 9 times 10 to the 9. That should be a times. And what we get is 9.3, we'll round to two significant digits, times 10 to the 10, 10 to the 9 kilogram meters per second. There we go. So that's our final relativistic momentum of this alien spacecraft, which, as we'd expect, because it's moving so fast compared to us, it's going to appear to have a higher momentum. The one thing to consider is, from their point of view, it's us that's moving by them. So from their point of view, our momentum will be increased, right? And their momentum will seem normal because their spacecraft isn't moving relative to them, which is an interesting thought experiment. So there you go. There's a bit of an insight into Einstein's understanding of relativity.